All right, hello. Welcome. This is the second of the two videos on nuclear energy. Hopefully we will have time to come back and do the story time thing at the end. I want to go through our radioactive decays first, though, because that's kind of the core thing. So there are 4 types of radioactive decays, or 5, depending on how you look at things. They were named in the order we found them: alpha, beta, gamma, chi, which we'll talk about chi in a minute. Alpha decay is simply the first decay that was discovered. The reason it was the first decay that was discovered is because it's really easy to see. Alpha decay emits what's known as a helium nucleus. It is 2 protons and 2 neutrons together. They get shot out of the nucleus to change the proton to neutron ratio in the nucleus. Now, this sounds like it shouldn't do that, but technically it released more protons than neutrons if you look at the ratio. And that's a thing. Hang on, my computer is complaining at me. Go away. All right, that is a thing that we're not going to mess too much with. You do need to know that an alpha particle, which the particle is the thing that comes out, is a helium nucleus. Okay, alpha particle is a helium nucleus. So if I say, what's an alpha particle, you need to be able to tell me it's a helium nucleus. The next one discovered was a beta decay. Beta decay emits a couple of different options, but both are leptons. So the definition for a beta decay is the emission of a lepton. So a beta particle is going to be an ejected lepton. So there's that. 2 kinds of beta decays, beta plus and beta minus. Beta minus, much more common than beta plus. That's why we didn't know there were 2 for a while. Beta minus decay is an electron getting shot out of the nucleus. That's why it's called a beta minus. Okay, because electrons are negative. And I have just realized I kind of skipped right past something. Leptons. Okay, we talked about quarks way back when we were doing atomic structure and protons and neutrons and all that. There are 3 fundamental kinds of particles: quarks, leptons, and bosons. Okay, leptons are the smaller of those, technically. Quarks are basically just heavyweights. Leptons are lightweights, and then bosons may not exist. And that's all I'm going to say on that. You need to know that electrons are leptons. That's why electrons are so much lighter than protons and neutrons, because they're not quarks, they're leptons. The other beta decay is a beta plus. Beta plus decay is the emission of a positron. Now, you might be going, what the heck is a positron? That's not something we ever talked about before. It is not the same thing as a proton. A positron is an electron with a positive charge. And for those going, how does that work? It's antimatter. Positrons are literally antimatter. It doesn't work, but the math makes it work. So it doesn't follow the same rules as matter does, because it's not matter. It's literally antimatter, which is a whole other debate that we're not going to get into in this class. So beta plus emits a positron. Beta minus emits an electron. Those are an electron. You know what an electron is. Positron is an electron with a positive charge, or an anti-electron. And both of those are leptons. Then comes gamma decay. Now, something I didn't mention about beta decays. Beta decays, as a side effect of this process, part of it that we're not getting into, causes protons to turn into neutrons, or neutrons to turn into protons. And then again, attempting to fix the proton to neutron ratio, it's switching protons and neutrons. Like I said, beta minus, much more common. We'll usually do alpha if it's trying to go the other way, but beta plus does happen. So what that means is you end up with a neutron, you end up with a proton that used to be a neutron. Well, if there were 3 protons around it, and now there's another proton right here in the middle, that area of the nucleus is extremely unstable, because it doesn't want that proton there. It's way too close to the other protons. Enter gamma decay. In a gamma decay, there is no particle emitted. There is no change to the nucleus of the atom, unlike these other ones. They change what's actually present in the nucleus. In a gamma decay, the nucleus just kind of rearranges. Think about it like taking a box of marbles and shaking it. That's basically all that's happening in a gamma decay. Except that as a byproduct of all these particles moving around, gamma rays, which are a type of lethal radiation that we'll spend more time talking about when we get to electromagnetic energy, gamma rays are released, which are dangerous. And again, we're not going to talk too much about gamma rays today. But gamma rays are emitted. There is no gamma particle, just gamma rays that come out. So the nucleus rearranges, but there is no actual change to the composition of the nucleus. And that brings us to electron capture, which was one moment. All right, it's been about a half an hour, so I hope I remember correctly where we were. I'm pretty sure we were on number 4 here, electron capture, or originally called a chi decay. Chi, which is another Greek letter, so like alpha, beta, gamma, and then chi, was the last form, I believe, to be discovered. Actually, I think technically beta plus was the last one, but we'll go with this. Okay. It was originally called a chi decay because it emitted chi rays. That was how we discovered it. There's no particle emitted, much like gamma decay. It emits rays. So an electron in this case is being absorbed into the nucleus or captured. And we called it a chi decay because we were detecting chi rays being released. Now, to most people, though, a capital chi is an X. And so instead of being called chi rays, they're now called X rays. And so instead of going with an X decay, we just changed it to electron capture. So yeah, in electron capture, an electron is being grabbed by the nucleus, pulled in, and it does stuff that we're not going to worry about. And as a result of that process, an X-ray is emitted and shot out of the nucleus. And that's the last decay. So I'm going to wrap that there. I am going to go ahead now and talk about our stories that I mentioned up here. So remember, all of this was stuff that happened in the Cold War. So the Cold War was us and the USSR. And intercontinental ballistic missiles, or ICBMs, were not a thing yet. The only way to nuke someone was to fly a plane over, drop the bomb, and then fly away. And that's how we nuked Hiroshima and Nagasaki. So the question became, oh, hey, the Soviet Union now has nukes. What are we going to do if they try to nuke us? Because if we engage their bombers and start trying to shoot them down, they can just launch their nukes early, drop their nukes early, and bomb maybe a different city. So how do we stop them from being able to do that? So someone had the idea, well, how about we put a rocket on the back of a nuke? Why not? It could work. And so the idea was you generally fly in formation, so there's multiple planes. So if you take one out, there's 4 or 5 others that can still make it. So we stuck a nuke on a rocket, or a rocket on a nuke, probably more accurate, and we would fly a plane up, fire the rocket with the nuke on the end, and when it was close-ish to the formation, we would detonate the nuke, and the nuke would take out all of the planes, causing them to fall out of the sky, be incinerated, whatever. And hopefully the nukes that they're carrying don't blow up. But that's our coping mechanism. That's how we're going to deal with these nuclear bombers if they should come to the United States. We're just going to blow them up with a smaller nuke. And we did it. I mean, not did it like in warfare, but we built this thing. We tested it over and near American cities. And the American populace went, no. We don't like, no, you're not, no. We're detonating nukes in the atmosphere on purpose over the United States. No, we're not doing that. And the government, specifically the military, goes, no. This is super safe, and we're going to prove it to you. So they took 5 volunteers, parked them out in the middle of Nevada, in the middle of the state, Nevada, and they detonated one of these nuclear interceptor missiles directly over their heads. I say directly, like straight up. It was about 10,000 feet at flying altitude, where these bombers would theoretically be flying. They detonated one of them over their heads, and they had these 5 guys standing on the ground, one of whom had a voice recorder, and he was talking into while it was happening. I do want to mention, because this I think is incredibly funny, the 5 military guys all volunteered to be there. The cameraman found out shortly before they launched the missile that they were going to be detonating up there and not over there. He was used to being a couple of miles away from it. This time he was a couple of miles beneath it, which was a little different. But apparently he said he was fine with it because he was used to filming it, and he figured, what's the worst that could happen? So there is actually a video recording to this. It should be linked on Canvas, so you can look that up. It should be the 3rd video that's linked in Canvas, hopefully, I think. That will show you that, so you can kind of watch that. It's about 2.5 minutes long. Only the first minute and a half really matters. The rest of it is all like wrap-up stuff, propaganda stuff. The other nuclear test is, believe it or not, after this, after we blew up the bomb over the soldiers, the American populace still was not sold on this whole detonating nukes in the United States thing. And so they switched to underground testing instead. So I want to talk about 2. The first one was, they drill a deep hole. They want to test their safeties that they built into this nuke to make sure it doesn't go off when it isn't supposed to. For example, we have a nuclear bomber flying over the United States. Someone shoots it down. We don't want the nuke to detonate on American soil. So there's supposed to be safety mechanisms built in to make sure that doesn't happen. So we dig a deep hole, put a nuke down there, and we put a normal bomb down there with it. And then we have a plug that we put in the top with holes in it. We can run sensors down so we can watch and read what is happening. Guess what? The nuke went off. It wasn't supposed to, but it did. And it fried and incinerated all of their sensors. So they said, okay, cool, that didn't work. But this might actually be a good way to contain radiation if we start testing underground. So then they come in, they dig another hole, put a nuke at the bottom of this one along with a conventional explosive, and instead of putting a plug in the top with holes in it, they take a 2,000-pound manhole cover and weld it into place above or at the top of the shaft where the nuke is at the bottom. And then because somebody, for some reason, decided to, they set up a camera over there to watch the manhole cover so that we could see what happened to the manhole cover when it goes off. Now, the idea is the manhole cover contains the radiation so nothing gets launched into the atmosphere, because that's what all those silly civilians were worried about. So they do it. The manhole cover gets ripped off the top of the shaft instead of flying. They see the mushroom cloud, and so they go to the camera, and they go, okay, purely for scientific reasons, how fast was that manhole cover moving? And so they look at the footage. The camera was set to record at about 1 million frames a second, which is pretty top of the line at the time. That means it's taking 1 million pictures every second. The manhole cover is in one picture. It's not in any of the others. Nothing before, nothing after. It's in exactly one picture. And so because it's only present in one shot, they cannot determine how fast it was in fact going. But they can determine how fast it had to be going to only be in one picture. So they can determine its minimum possible speed. And they calculate that speed to be 135 million miles an hour. The manhole cover came off the top of that shaft at 135 million miles an hour, and quite possibly was actually the first artificial satellite. We don't know that for sure. There's a lot of debate about whether it actually made it all the way through the atmosphere, or if it would have been incinerated like meteors that are coming down, or if it would have made it all the way through and gone God knows where after it got out of the atmosphere. But yeah, so that was the nuclear manhole cover. So if you ever see reels on Instagram or TikTok or wherever you're looking, and they talk about the manhole cover in space, that's what it's talking about. It's talking about this. FYI, they actually did this twice. They didn't do it just once. They did it twice. I'm not going to go into that, but yeah, I thought that was funny. So that's where I'm going to wrap this video. Have a wonderful day, night, week, whatever it happens to be, and I'll see y'all next time.